I'd like to introduce myself. My name is Dave Michael. I teach science here at Bluff High School. And 5 years ago now, Bluff High School, along with Lassen Volcanic National Park and NASA Ames Research Center down Mountain View, entered into a very unique partnership. And this partnership has continued and really flourished in the last 5 years. It's unique simply because it's the only one like this in the United States. Bluff High School is the only school involved in a program like this. Lassen Volcanic National Park is the only national park involved in a program like this. And then NASA Ames is the only NASA Research Center, I believe, involved in a program like this. So it is truly a one-of-a-kind program that we have here. And what it really is we've created what we call an astrobiology program. And what goes on is our students here at Red Bluff High School have worked hand in hand, shoulder to shoulder with scientists from Ames Research Center conducting research up at Lassen Volcanic National Park. And what it's allowed everyone to do is develop a better understanding of the park and really to gain a greater appreciation for the realm of science. And so it's very unique in how we do things, and it's been very productive in what we've accomplished. Our students really have gotten three things out of this. The first is they've gained experience. And when I say experience, what I mean is in the classroom as teachers here at Red Bluff High School, we show skills, we teach knowledge to the kids. But a lot of times they don't see the connection to the real world. A very common question that teachers are often asked by students, when am I ever going to use this? Well, this is the when for these students. These students are basically going out to the field and using the knowledge that we're teaching them in the science classroom and actually getting the skills and the experience while using that knowledge to go further on in life. And so they're really just gaining a tremendous amount of experience doing that. The second thing that they're getting from this is an overall knowledge and appreciation of Lassen Volcanic National Park. When we're in school, we break down science into biology and chemistry and earth science, and we have these set curriculums based on our specialties. When we go to the field, studying an area, there is no set specialty anymore because there's so much overlap. And what they're gaining is an overall knowledge of how science works, how all of these fields blend together, and only through that blending and that understanding can they gain a true appreciation for what's going on up there. And so it's a real knowledge-based education that they're getting. And then the last thing that they get from this is they get a tremendous new perspective. And this perspective comes from the scientists that they work with. They're gaining a perspective on the world outside and after high school. They're gaining an appreciation for careers that they can pursue in science, majors that they can major in college. They're gaining a tremendous experience with some awesome role models as these scientists, people that are highly professional in what they do, but also they get to see that just working at NASA doesn't necessarily mean that you're a rocket scientist that can't relate to people, and sometimes, I hate to say it, NASA, that's what we think. Okay? You look at it, go, NASA, you're not a real person. Okay? And we see that that's not true. Okay? And what we've been able to expose our students to is now they have the very real understanding and the very real desire that they too could someday work for NASA, or they could someday get a career in a science-related profession, something like this. And so the benefit to these students is truly remarkable. Because of this, Red Bluff High School is obviously very, very proud of this program. We look forward to continuing this program for years. Look forward to these students moving on and new students coming in and learning from them, and just overall just gaining a thorough understanding of not just Lassen Volcanic National Park, but also the science process. It's a really cool thing. So right now, what I would like to do is introduce to you Ranger Steve Zachary, and he's going to come up and talk a little bit about this program from the Lassen Volcanic National Park's perspective.
Thank you, Dave. Well, I'm, of course, proud of all our students and have been for a long time. This program actually sprouted in 2007. In 2007, NASA, Ames, invited national park educators and interpreters down to Ames to discuss how we could build a partnership involving education and outreach with national parks and NASA. So I attended that. I was at the Ames Moffett Field Research Center for a few days, and we went over opportunities and what could be done. And of course, Lassen, in relationship to what's going on with NASA, was a perfect fit. You know, we've got hydrothermal areas, we've got volcanoes, and so it sprouted right there. And then they were saying, well, how can we get these students, how do we get students involved? And believe it or not, this summer will be the 18th year that I have run the high school interpretive intern programs, where high school students such as these come up and work at Lassen National Park. And first, when I started this program, which started only with Red Bluff High students, the Park Service in Washington, D.C. said, oh no, interns, they have to be over 18. Oh no, you can't have younger interns. What do you mean? And I said, why not? So I said, so we took on the responsibility. I took on the responsibility with a few other people, and we set up the interpretive intern program to sign up high school students as volunteers with the National Park Service, and for them to work and have experiences similar to what the astrobiology interns do in the summertime at Lassen. So that has gone really well. Like I said, this is going to be the 18th summer of this program. In fact, this year, I've tried to hold back. You can imagine if you were in charge of, this year I am in charge of 21 students. And now, you know, they're from not only Red Bluff High, we have students from numerous high schools here in Northern California. So that, again, sprouted the concept of, well, when we talked about doing an astrobiology intern program, we just set up the same template for developing a position description and taking care of all the government paperwork with the National Park Service. So working with NASA, all the students are signed up as National Park Service intern volunteers, which means that they, in the federal government, all work experience, paid or unpaid, counts. So all the experience they're getting here, and same with my summer ones, that counts as federal job experience. So over the years, and I have been able to also, when those students went to college, just like these students will, then I've been able to hire them, and they outcompete a lot of other students because here they are, they're just turning 18 and they already have job experience with the federal government. So that has helped us in getting the astrobiology intern program on fast track once we started it, which has been almost 5 years now. And they, just like all the hours that they put in here with this program, they will get credit with the federal government. And when you think of knowledge, skills, and abilities that we all need and have to have in order to compete in the job market, you know, the knowledge, skills, and abilities that they have gained from this program, as some of the other things that we do, is just amazing. In fact, 2 of the students this summer, or that are in the astrobiology program, Marissa and Lily, they're saying, hey, sign me up for the summer program too. So, you know, it really has some great ramifications and benefits for everybody, and that's, and the astrobiology intern program has just been wonderful in carrying forward all those goals of involving high school students in real science and working with NASA and working in a national park such as Lassen. And since it fits so well because, you know, Lassen obviously is in the backyard here. So it's just been perfect, and you know, I've enjoyed every minute of it, and will continue to enjoy every minute of it because they're my inspiration. You know, the bureaucracy and all those things that happen in the federal government. You know, I can bypass all that and say, hey, look, you know, look what it's paid off in working with these students. And so it's been a real pleasure working with all of these students, and we'll continue to and try to help them in writing letters of recommendation and helping them support them in their future. So I'm really proud of what they have done and accomplished, and to support parents, the communities in making this program happen. Because it's also, you know, especially in those under the age of 18, you know, we have to have parent buy-in. I can't, you know, if you're over 18, I can sign them up, but I have to have parent buy-in on all of these programs, and thanks to you, this has been made possible. So, and on that note, I will turn it over to Dave Morris.
Did I make it under the, just barely under the line?
Series of jobs I have to do to set the context for the report that we'll hear from the students. First, I'd like to provide a little background about Mars, sort of the history of our exploration and some of the details that will be handy. Second, to sort of try to establish this connection between why Lassen is such an important thing for us as a study object for understanding more about how to go about Mars exploration, and to provide you enough specifics in that so that you can get a sense for the context of the project that the students had this year. And so just to give you a little bit of a roadmap, I thought I would point out some of the key things that I want to address tonight. And that is that the Earth and Mars are similar in some very important ways. They're both rocky planets as opposed to the large outer planets, Jupiter, Saturn, and so forth. And they have geologic processes that are in many ways common. And the key one, of course, and this brings the connection to Lassen, is the volcanism. Both planets have, the surfaces have been extensively landscaped by volcanism. And this carries ramifications beyond just the landscaping. It gets more into the details of looking for evidence of life there. And related to that, water activity is something that probably motivates us to Mars as much as anything beyond the Earth. We definitely have evidence that it was there in the past, big time, and we're learning more about that every year. The question about activity today on Mars is still a question mark in many ways, but interesting nonetheless. The key thing is that Spirit rover found an ancient hydrothermal system on Mars a few years ago. And of course, by hydrothermal, we mean volcanic activity interacting with water. So these two key characteristics here, the activity of water and volcanism, come together in what we call hydrothermal activity. And the key point here is that this could well be a kind of activity, a kind of locus in an environment that could be very important for establishing habitable conditions. You'll hear more about that tonight. More recently, Curiosity rover confirmed the presence of clay deposits, or phyllosilicate minerals. What are these? Well, they're important because they represent an alteration of volcanic rocks by water. So again, water and volcanic rocks interacting to form this product called clays. Now, what's interesting is that clay deposits on the Earth can preserve fossils. So there's a connection here between very important processes in the planet and the fact that these deposits that are a result of that could be repositories of information. So how do we interpret this record of clay deposits on Mars anyway? Well, we perhaps study similar environments on Earth, and that brings us around again to Lassen. So this is sort of the overview of the talk, and I'll just try to hop through here. Now, to start off with, this concept of Earth and Mars having similar environments is not a new concept. For those of you who know about the history of the concepts about Mars, this is the famous map that Percival Lowell created, he said, from his astronomical observations, telescopic observations. And some of us today are still debating that which of these features might have actually been real. Some of them, one of them we know is Valles Marineris, but others could have been wind streaks. In any case, this human desire to have Mars be a place so much like Earth really drove his thinking. And I want to make a key point in this first few slides. and that is how Mars exploration has been yet another example of the incredible explosion of our knowledge and our technology in just the last 100 years. And when you go back through and just see what we were thinking about Mars during the periods of the past 100 years, it just makes you realize the incredible advances that we have made in such a remarkably short period of time. This was 100 years ago. Just 100 years ago, there were no independent checks on his interpretation, and that then was really the prevailing view of Mars. And as if that's shocking enough, you go to 1938, and you have not only, of course, the Mars of H.G. Wells, but the famous radio show of Orson Welles literally freaking out the entire American public that we were about to be invaded by Martians. And this is what their civilization looked like. Okay, there's the Canale coming from Percival Lowell. These amazing cities, again, human imagination, sort of extrapolating beyond the really very limited knowledge we had of Mars as late as 1938. Now, when we get to 1955, the telescopic observations are getting better, and we're bringing back the news that the atmosphere of Mars was a lot thinner than what we had thought, not as down to what we know it is today, but thin enough that where a very famous artist, Chesley Bonestell, still has those canali in there. You know, good old Percival lives on, but he had algae now growing around these canali. The cities are gone now. They figure that, wow, you know, by the time of these observations, we can't be throwing cities up in the landscape. Perhaps if there's any life there at all, and of course people still in the 50s wanted to believe that there was life there, maybe it's algae growing next to these channels. He has this now. Of course, then there was the discovery of the polar caps on Mars, so he's got a little bit of ice down there to finish off the picture. 1955, we're halfway through the century now, coming up to the present. And it really gets into the 60s when we really get close enough to Mars to get a much more realistic perspective about it. But in a way, it had an interesting effect. As you know, we're building up to lunar missions at this time, and suddenly this flyby, this Mariner flyby, shows all these craters, and for all we know, another moon out there. And so suddenly the stock market on Mars crashes into the Great Depression. My gosh, this is just another place like the moon. There's no atmosphere, the craters are on here just like the moon, and this was sort of the low point. We knew just enough to be dangerous to the conclusion that maybe it was just like another moon, and that was sort of where the stock market hit the bottom. But of course, the observations that follow move us now into what I call space age Mars, and that is a Mars that now is becoming more and more interesting. It's turned that corner and the market's rising. The more we learn about Mars, the more we begin to see really functional similarities and details between Mars as we're beginning to understand it today and the Earth. These, by the way, are clouds that are forming around the summits of some of the major volcanoes on Mars. And so there really is a dynamic atmosphere with vapor condensation and cloud formation and all of that. So some of the details, and that is that you know, Mars is considerably smaller. It has only 38% the gravity of the Earth. Its year is about 2 Earth years. But the amazing thing, the sunlight, it's only 44% of that reaches the Earth. But really, that's not a substantive deal. The sunlight on Mars, if you had other conditions just right, would be just fine for photosynthetic life. The axis of the spin axis is very similar to that of the Earth, which means seasons on Mars are rather analogous to the seasons that we have on the Earth. Equatorial climates being the way they are on the Earth, analogous to that on Mars. Atmosphere is quite different, a lot less, only 7.6 millibar. The Earth is 1,013 millibars, and of course the atmosphere of Mars is 95% CO2, and we all know nitrogen and oxygen dominate our atmosphere. Here's an interesting statistic. You want to explore Mars? Well, the whole surface of Mars is equal to the surface area of all the continents on the Earth. That's a lot of territory. Okay, so how do we then figure out a way to explore Mars, look for the sweetest little spots that really, given the precious and very rare nature of our ability to get to the surface of Mars, how do we optimize those opportunities? And that's what preparing for exploration for Mars is all about. Just notice this little statistic here, that the land area of Africa is about the same as the total surface area of the moon. So there's another cocktail hour statistic for you. a lot of similarities really between Earth and Mars. So to get to that, and just to make that point more, here's now is a Mercator projection of Mars. We all know what Mercator projections of the Earth look like. But I show you this. These colors represent elevations. Highest elevations are these huge volcanoes on Mars. By the way, another similarity with the Earth. It has volcanoes, as I mentioned. And then the red colors are more the southern highlands, whereas when you get to the lower elevations, you get into the northern lowlands and Hellas Basin, a huge impact basin in the southern hemisphere. The point is, Mars has what we call a crustal dichotomy, and that is it has a fair amount of its area at a typical characteristic higher elevation, and another major part of its surface area at a characteristic lower elevation. And so we call that a crustal dichotomy. The distribution of elevation is bimodal between the southern highlands and the northern lowlands. So we have the southern highlands, northern lowlands, we have volcanoes, a number of features to point out, and really what I'm setting you up for is now to show you the Earth. The Earth has a crustal dichotomy. We call them continents on the Earth, and we call both basins, we call those ocean basins, but that's the lower dichotomy on the Earth. But more to the point, if you look past that water, you're looking at a volcanic province. 70-some% of the surface of the Earth is a volcanically active province. Earth is a volcanic planet, bar none. I mean, it's incredible. And in that sense, it's very analogous to Mars. That's all lava flows. These are huge deposits and a big lava domain here, and there's another one over there. But Mars is a volcanic planet dominated by basalt. Earth is a volcanic planet dominated by basaltic flows. It's just you can't see most of them because they're underneath the ocean. So a very important analogy between the Earth and Mars. And to sort of stress that point today, these are pictures that were just taken earlier today. We went into a lava tube up in the north, just off the northwest east, east side of the park, I guess it is, the subway cave. It shows the entrance and the students, and there's Mr. Zachary providing some introduction to it, and here they are again. Just to show, and this is a process of lava flowing along, the top of the lava flow becomes encrusted, the bottom part keeps flowing, and you end up with a nice open cave. We've excellent evidence that there's probably these lava tubes. We know they're on the moon, and I think students, I think in Cottonwood,
Evergreen
Middle School have discovered lava tubes on Mars. So kids are looking at these images of Mars. And again, documenting the importance of volcanic activity and the processes happening. So here we have it. We have basically lowlands dominated by volcanic plains, lowlands dominated by volcanic plains, highlands, we call them continents on the Earth, southern highlands on Mars, volcanoes in both planets. A lot of analogies, okay? So this is encouraging because perhaps we can now take this next jump, and that is that when you go to the early history of the Earth, based on the rocks we find on those continents, which by the way preserve the oldest rocks, that's another key point I wanted to make. The oldest rocks on Earth are preserved in the continents, the oldest rocks on Mars are preserved in the southern highlands, and you can see the craters indicating the great age of that surface. So the early Earth, dominated by volcanism, water, and just a whole bunch of associated features, the hot springs, all that. We see evidence for all of this in the Earth's record. When you go to Mars, you see these huge volcanoes that were most active in that early period, and there's excellent evidence that that activity, being much greater in the early period of Mars, created a climate dramatically different from today. How do we know that? We look on Mars and we see an evidence of huge river channels flowing from the southern highlands into the northern lowlands. And this, you can see a scale bar here, 50 kilometers, huge river system flowing down from the southern highlands into the northern lowlands. Huge volumes of water erupting from the subsurface, creating what we call chaotic terrain, and then the water flowing off. These are huge channels. It's not just the length, but just think of the diameter, the cross sections of these things. A lot of water moving across. As our remote sensing data have gotten better with Mars, we can now begin to populate those southern highlands with features that are crater lakes. There's a lake and a crater that's at each of these locations, and we can see the strand lines around the side and other evidence that water was in there. Look at the distribution of these things. The only place you don't see them is a place where lava flows covered them sometime later. All these funny squiggly features here, each one of these is a well-integrated stream system with channels coming together to form larger channels and so forth. So it's beyond a shadow of doubt now that sometime in the distant past, there was precipitation on Mars. It rained on Mars, and probably maybe associated with seasonal change, as you see that these are mostly clustered around the equator at this dichotomy boundary between the southern highlands and the northern lowlands. So it's now obvious that the early climate of Mars supported liquid water at the surface. It was running all over the place. And so the early Martian environment was much more Earth-like than that of any other solar system planet. And that's why I think, in many ways, early Mars just really captures our attention. This is, by the way, an artist's concept. Again, this is again Percival Lowell stuff, right? I mean, we haven't proven that. But the idea is that that could have been possible. And there is some evidence that's consistent with it. So indeed, moving along then, let's try to see what this means for certain key environments. In fact, at the Spirit rover, now let me talk a little bit about what we mean by habitability, and you'll hear more about this later. It's not just that water was present in a certain amount and concentration to support life. You also have to have a source of energy, which we take for granted because we have sunlight, we have beautiful green trees and grass and plants and crops out there. But you have to have a source of energy of some type, and you also, of course, have to have the ingredients. Now, the food we eat, the nutrients that you give a plant to fertilize it, and so forth, all those things come together to give you a habitable environment. And we demonstrate on Mars that all these things came together in a nice way to support life. Well, that's our challenge, one of the reasons that we design these missions the way we do. The students are confronted with the same thing. Can they go to a place and prove that that's a habitable environment? Okay, well, Spirit rover, and of course you've seen this image many times, it's designed to be a robotic field geologist with its eyeballs and wheels to be able to move around, and an arm to manipulate and do analyses and so forth, communicate back to Earth, solar power, all the kinds of things you need to operate on Mars for 8 years now. It's pretty amazing. This rover is no longer with us, Spirit, but it went to this place called Gusev Crater, where a major stream channel flows into what was one of these crater lakes, and then it overtopped and flowed into the northern lowlands. For good measure, here's Apollinaris Matera, a volcano nearby. So again, this is a province where we have evidence of geologic activity and volcanism, as well as this evidence of liquid water. So these are all the ingredients we'd like to bring together: the water, the geologic activity, and so forth. And that was Gusev Crater. This is again a National Geographic Society artist giving you a sense of maybe what this place looked like 4 billion years ago, with that stream coming into that crater lake, water overtopping, flowing out into the northern lowlands at the distance. Did this really ever happen? There's good evidence that it did, but can you go to the ground and find the deposits? Well, unfortunately, we went to the ground and didn't find those deposits. We landed on a huge basaltic lava plains, okay? But we saw these funny hills off in the distance, and there's a picture of them, and thought, you know, these look different, maybe they represent older deposits. Let's go over there. When we went over there, we went into an interesting place called the Inner Basin. That would have been this area down in here. We sort of went up this hill, did a lot of things, and then went down into this inner basin. And when we went into this inner basin, we saw volcanic rocks all over the place. We said, well, this is exciting. Then we found this weird pancake-shaped structure called home plate. Looks like home plate if you're into baseball. And it's about 90 meters across and about 1 meter or 2 high. And when we went there, to make a long story short, it was a major revelation. Here's home plate, about 90 meters across. But what we found there were not only the basaltic rocks with a lot of holes in them, which means, by the way, a lot of water coming out of this basalt as it's erupting, but we found evidence of pure silica deposits, just like you'd see around Old Faithful Geyser at Yellowstone. And we found evidence of salts, sulfur salts of iron and magnesium, which pretty much indicates that we had hot acidic fumaroles steaming away with sulfur coming out, oxidizing and altering the rocks to give you these iron and magnesium salts. And so evidence of hydrothermal activity, not only the thermal activity with the volcanism, but the water interacting and altering the rocks, much as we would see at a place like Lassen or Yellowstone. Now, I wrote a paper several years ago with Malcolm Walter where we said, you know, boy, if we could find something like this on Mars, this would be great. Here's a source of water. Here's some chemical species coming up from the spring that could support life both as a source of energy and as nutrients. And there's just a number of other reasons why this would just be a great place to look for evidence of life on Mars. And perhaps we've now maybe found this. Okay, so that was very exciting. And again, that's what really motivated us to start this study with the students here at Lassen. But we go a little step further now. We're talking about the rover that's now very much active on Mars. In fact, we're now just starting up operations next week after Mars has gotten a little bit away from the sun there on the other side of the solar system. We can communicate with it again. But we found the evidence of these clay deposits. Again, water alters volcanic rocks to form the clays, and these are a potentially great place to look for evidence of fossils. So here's Gale Crater, a pretty big crater, 170 kilometers across. Here's Curiosity rover. I won't spend details describing that, but it's another one of these robotic geologists that can move around, has eyes, instruments for analyzing, much more powerful instruments really than the ones we had with those smaller earlier rovers. And we just set to be, what we were really excited about was this big Mount Sharp mountain that's in the middle of this crater. It had all kinds of layers of rocks. It's a very old crater, and it could have a nice geologic record of a lot of what the early environment of Mars might have been like during a period when we think there was a lot of liquid water involved. So a very exciting place. We'd love to get close to that mountain, but we have to land out here where it's nice and flat. And quite frankly, that's where we still are right now, but it's not been time wasted, I can assure you. Here's where we landed, and when we started to drive, here's where we landed. This blue is where the rocket exhaust has blasted away all the dust that was on the surface. And then we migrated over here. You can see a scale bar here of about 200 meters. Over to the east, and then down into a place called Yellowknife Bay. And we went down in there because we see these funny layered deposits that have fractures in them, and they look very reminiscent of a lake deposit. And there's just some evidence that there was standing water in this moat surrounding the mountain at one point. And we thought, well, what a great way to test out the instruments and validate that they're all working. Go look at a very interesting deposit, which we did. Here we are now down in Yellowknife Bay looking at this sort of mud crack looking type surface. Even some funny vein-like structures sticking up out of these rocks where the softer material between the veins has been eroded away. And here's the arm of the rover now going out, and this is the first drilling that we have done now with this mission. This was done about 2-3 months ago. Drilling down into this material to see what it's really made of. And some of the pictures coming back to this rover are just amazing. Here's our first test drill hole. Okay, that's a couple of centimeters across, a little bit less than an inch. And then here's the one where we mean business. We drilled down to about 6.7 centimeters into this stuff. And we were immediately excited by this because now instead of having an oxidized red color to this that we see on the surface, we're looking at a nice gray-blue material coming up from below. This is a sedimentary rock. It looks like it's been altered by water, and it's not been oxidized. The stuff that's in there has not been destroyed by this oxidizing surface environment. There's all kinds of things I can say about this deposit, the ability to sieve material and to dump it back and analyze it on the surface. This rover has amazing capabilities for processing samples. But this next sort of kaleidoscopic, well, this is now the picture of the sample going into the big instruments that are inside. One of the instruments we have right here in the back, it's called Terra. This is Chemin on Mars. It's an X-ray diffraction instrument that can do elemental analysis as well as the analyses of minerals, even a mineral we've never discovered before. This instrument, that instrument, has the capability of identifying that. A very powerful instrument for determining what kind of environment had to exist to form the minerals that we find. And we can give a little demonstration of that. Dave Blake, the fellow who invented it, he also has this. This is a commercially available instrument, but it's exactly the same concept as the instrument that he built for this mission. This is very important because this is the mineral. This is the instrument that can identify whether we have a clay mineral on this thing. Now, for those who are familiar with X-ray diffraction, you know that each of these lines, as measured from the origin, represents a distance between layers of atoms in the lattice of the crystal. So just as you drive by an orchard of trees that are all lined up in rows and spaced evenly, and you can look down, and every once in a while you can see all the way down a row, that spacing that you're seeing is analogous to a spacing that we see as we go up through here. And you'll know if you're driving by the orchard and you're looking at different angles as you go by, you'll notice you'll see different features as you look at various angles. Next time you drive by an orchard, you haven't done it before. And that's very analogous to looking into the crystal lattice of a mineral. And the spacing that you see as you look at these different directions is the spacing that we're showing here on this diagram. And that is a unique fingerprint for that mineral. Okay, it's amazing. There are tens of thousands of minerals, but by doing X-ray diffraction, you can uniquely identify what that mineral is. And that's exactly what you're looking at. Now, clay minerals are characteristic because they're very flat laminated minerals, and in that one planar direction where these flat layers of clay minerals are oriented, that spacing between those plates is really big. And just the way it happens to work out, that shows up as a very small value here. Actually, it's sort of inverse. This represents a very large spacing, and these represent smaller spacings. But the point is, this cloud here that you see that you don't see in this unaltered rock. This represents the presence of clay minerals, and this demonstrates that that drill powder had a substantial concentration of clay in it. So we have now conclusively proven that there are clays on Mars, which are it's very exciting because, as I said before, on the Earth, clays can be a great repository of fossil information. Of course, that's not proving that there's fossils there, but it's like the place to look. You know, it's hard to find a needle in a haystack, but if you know that there's a needle in the haystack, you start looking in the haystack. That's the haystack right there. So that's a much smaller haystack than the entire surface of Mars, which again is all the surface area of that land on the Earth. And so already now we have found the right place to look further for that evidence. And this is getting pretty technical, but I'll say we can take that same sample and put it in another instrument, heat it up. And this is just temperature here. We're heating it up hotter and hotter. And all you need to see is that when we heat this up, we get water up. At a higher temperature, we get carbon dioxide, then we get oxygen. That's weird, didn't expect that. Sulfur dioxide, hydrogen sulfide. The point is, this is proving that that deposit has locked in water. It's locked in something that's giving us the CO2, something that's giving us these other gases. It's giving us the kinds of chemicals that are the stuff of a fossil record, or the stuff of a record of an early environment that was rich in water. So we don't have the molecular detail here yet that tells you, wow, you know, I see evidence of life here, or I see evidence of organic matter. But you do see evidence of the ability of this rock to preserve something of great interest to us, whatever that story might be about the environment. And so what we now have learned from our observations of Mars, and this is sort of a diagram of the early history of Mars moving along to the present time, that we had an early environment at the surface that was very Earth-like, and that it deteriorated over time to the environment that we see today. But in that early environment, this green represents clay minerals and other deposits that formed, that had the potential to have preserved a record of whatever it was back then. And if that was life, wow, that's great. If it wasn't life, well, now we know. But we do know that we have a record preserved in the clay minerals of whatever the heck that environment was like and whatever might have lived there. And that's the major discovery that this mission has made. And so here's now the future of this mission. Once we're done here, we will drive towards Mount Sharp, which is an enormous mountain, and that, by the way, would be the size of our rover that was in that picture. A little tiny speck there. Yeah, these layers are like a history book of the early history of Mars. And for those of you who've been to the Grand Canyon, you know that when you hike into the canyon, you go by layers and layers of rock that literally represent 1 billion years or more of Earth history. This is the scale of Mount Sharp, and it's another 3 kilometers above that, with the very characteristic layers that we see in there, including, we think, evidence of clay minerals. And that's a history book waiting to be read. But how do we read it? You know, it's nice for you to have a book in your hands, but if you don't know how to read, that book can't tell you very much. How do we interpret the record of Martian clay deposits? Well, we start by looking at environments on the Earth that might be analogous, and that's where Lassen comes in. We ask the question, are there deposits or places on Lassen, in Lassen, that satisfy the energy, water, and nutrients thing that could be places for microbes to live, and therefore that makes it a great natural laboratory, and your students here are the explorers who are going to tell us more about those details. So with that, thank you very much, and let me just finish with the final picture here. It's really a bizarre picture. Thanks for your how much time? I think we're...
Let's do the questions at the end.
Yeah, let's do questions right over.
Well, we're just getting things ready to go. First off, wow. As you can see, our students are exposed to a tremendous amount of knowledge. Okay? Dr. DeMarais has, and then Dr. Parentow and Mr. Kudo, our students have been exposed to the intelligence that all of these scientists bring. Now, 5 years ago when this program started, 5 years ago when this program started, basically our students, our interns, were simply going out, receiving training, and then taking measurements. And as the program has changed, you're really going to see quite a difference here today. Now our students are not just trained, don't just take measurements, but Before they do that, they conduct research. And they also make observations. And then they gather data. And then you're going to see and hear from them today some of the conclusions that they've come up with from this. What we've asked these students to do is really college level work. We've asked them to come up with a thesis, write a thesis paper, and they presented this paper. And today what you're going to see is a compilation of not just their individual papers, but the group that comes together here. So they're going to talk a little bit today about their findings throughout the course of this year. So, right now, are we ready? Almost.
Do you need it on both
Funny
screens?
question.
Do you want it on both screens?
If you could do that, that would be so amazing. It's not doing full
Maybe
screen
one by
for
one.
some reason. I can't, oh, wait, never mind.
Good.
I'm good. Sorry, guys.
And so now I think.
Yes,
I think we are ready to go. So, you're up.
Okay, well, this is the Astrobiology Intern of the 2012-2013 year. As you can see, this is a group shot of all of us at Ames, at NASA Ames Research Center down in Lassen Field. Nice looking group, isn't it? Alright, so we're going to introduce the three groups that we split into. This is first the acidic group, so.
Hello, I'm Olivia, and I'm from the acidic group.
I'm Jessica. I'm also from the group. I'm Elena, and I'm as well. I'm Adrian, and
And there's two from the same starter, and we're the juniors.
This is the alkaline group, and where I'm the senior leader. My name is Justin.
my name is Adrian, and I'm a junior. My name is Mason, and I'm a junior.
My name is Kyle, and I'm a junior.
This is the neutral group, and I'm Lily, I'm a junior. I'm Carly, I'm also a junior.
My name is Marissa, and I'm also a junior.
Okay, so this year we took our annual trip down to the NASA Ames Research Center in Lassen Field. We were welcomed heavily by everyone there, as you can see from the sign, welcoming us as regular high school interns. Here are a couple group shots of us there in the wind tunnel. And as you can see in the lower right-hand corner, that's us on top of the roof, interacting with current running experiments there. We also took various amounts of field trips up to Lassen. One of them included a snowshoeing expedition that started at the very beginning of the Komiamani Visitor Center in the southern part of the park, and we snowshoed for about a half a mile to the entrance of the Sulphur Works area.
Okay, so what to expect in this presentation? What is astrobiology, and why Lassen, and also like what is habitability, and our field size and concerns and solutions, and the overall concerns.
Okay, what is astrobiology? You all may be wondering what astrobiology is since we are the Astrobiology Internship. Okay, so astrobiology is the investigation of the origins, distribution, and future of life in the universe. A key aspect of astrobiology is to search for and characterize the full diversity of habitable environments, both on early Earth and on other planets, and volcanic activity and its interactions with water are key aspects of this look for astrobiology within the universe.
Okay, so why are we interested in Lassen? The Lassen Astrobiology Intern Program explores how volcanoes, water, and life interact to sustain microbial ecosystem. The Lassen Volcanic National Park provides field sites where volcanic processes not only interact with water but also with they can host microbial life and at all spectrums of the phase scale. anomalous sites for the highly related Martian systems and
Okay, another thing is that Lassen provides some of the key requirements for life, which makes habitability and makes the planet habitable. So some of those requirements are a solvent, raw materials, favorable conditions, and energy. And the forms of energy are light or chemical, and light comes in the form of photosynthesis, and chemical is like us. We break bonds of organic molecules. A solvent can be water, and then raw materials can be carbon, hydrogen, nitrogen, oxygen, potassium, sodium, and electrons. And then the favorable conditions depend on the organism. It can range from a various degree of temperature, pH, conductivity, and the other thing that forms a condition for living systems.
So where did we sample? This year we had two key places in the park we sampled. For the first time in our history, we sampled in Warner Valley, which hosts various areas of both acidic and alkaline features as well as the neutral streams. And we also sampled at the Sulphurworks site, which is one of our key sampling areas for the past couple of years.
So the Sulphurworks site in Lassen wasn't so much about our experiment, it's about NASA's experiments. We helped and or hindered because we were really curious about what they were doing when they were taking samples up there. And we also did a satellite broadcast. We also did a satellite broadcast to different schools within the U.S. to kind of test out how their technology using satellites and bouncing beams work, which is also really, really interesting for us. It's also a great example that a lot of you have probably seen of an acid feature, a lot like what we studied in the acid group. Again, this is just more pictures. You can see in the top left, but a lot of what we were looking for. And picture broadcast.
Okay, so these were the various sites that we looked at and took samples from, which was up at Warner Valley, which is at the northeast corner of the park. And those pictures is where the acid group picture was from, the outline was, or where the outline group picture was from, Hill Creek and the Valleys, or where the group was.
You have to speak louder.
Okay, so one of our principal places that we sampled this year was Warner Valley Field Site. Like I said before, it was our first time sampling there in history. We took an overnight trip there and we set up, that is primarily where we split up into three different groups, the acidic group, the alkaline group, and the neutral group. And it hosts just a very wide range of aspects from both the acidic areas of Devil's Kitchen as well as the alkaline sites where we've sampled at the alkaline vent, and host neutral sites as well. Yeah, this is how we collected. In the top left, you can see areas from the snowshoe expedition. The bottom right, you can see the setup in Warner Valley, and then the top right, you can see one of the actual intern sampling in the field at Warner Valley.
The way each group went at their sites, collected measurements of pH, conductivity, and microbial samples. And in order to do this, we used a pH meter, conductivity meter, tweezers, a sampling syringe, bottles, a laser thermometer, so we don't have to actually put anything into the sampling. We also used Mr. Longarm during the winter times because it is unsafe to go into the sulfur pits with water. So that allows us to get into the sulfur pits without actually going in there. And we also used filters in order to filter out any other contaminants when we took cation and anion samples.
Nice.
That's an example of a conductivity meter that we used in the field. And that's an example of a pH meter which we also used in the field.
Very nice.
This is one part of our experiment. We had two parts. This part was the rock dissolution experiment where we took andesite, which is the dominant rock type found in the Warner Valley, and we subjected it to tests across the pH scale. We had an acid the group that put the andesites in an acidic solution, the neutral subjected it to a neutral solution, and then the alkaline obviously put it into a more basic solution. And this happened over a 3-month period, and we were trying to analyze what the trends would be and what would happen to the rock depending on the pH. Like acidic solutions are more, they're better at dissolving the solution to release nutrients into the stream for the microbes.
Sorry.
And then that connects to the microbe cultures because, well, we took the microbe cultures from each site, the neutral, again, neutral, alkaline, acid, and we put them in different media cultures depending on what they needed. The acidic ones were put in an acidic solution, media to help them grow, and we wanted to recreate basically the conditions we found in the field to see if we can, create life, the conditions for life, like hopefully what we would find on Mars. So.
So this is a picture of our acid freeze level station connected to all isotopes.
Okay, again, the 2 experiments for the rock dissolution and microbial cultures, and they connect because the rock dissolution, what we're seeing basically like how much of the nutrients actually get into the solution depending on what type of pH is in the system, and the microbial cultures. Yeah.
And with the microbial cultures again, it was the same thing for the acid experiment specifically.
We can't hear you back here.
Sorry. Just yell it, okay.
Just yell it.
For the microbe experiment specifically, in the acid group, we used one with sulfide and other nutrients that we would find at our field site instead of the other groups.
Okay, so in the acid dissolution experiment, we had an experiment set up with at 60 degrees Celsius. So to dissolve the rock into the solution, and the pH of the solution actually went up, so it became more basic from it dissolving into the solution. But it actually, the rock acted as a base, and it precipitated out some of the acid. In the microbial culture, the same thing, a sample experiment wasn't very successful because there wasn't enough of a power source, the sulfuric acid in the solution to make it grow.
But we did manage to grow, but we weren't trying to grow. So
Yeah.
that's always interesting, and it's not
Basically,
a bad thing.
the phototrophic microbes took over kind of in a way because they had their power source, they had light and all those things, and the chemotrophs did not. They couldn't grow because they didn't have their power source.
And for the rock dissolution experiment, because it was the neutral group, they were acting as our control group because they also had a 60-degree solution.
And this just shows the results of the experiment. You can see the trends in pH. The pH went up over time. It became more basic, and the specific conductance actually went down, which means there's less ions in the solution. And the total dissolved solids went up, which show that acid is more effective in dissolving the rock, or to again release the nutrients for the microbes, the chemotropic microbes.
Okay, to touch on that again, we had set up a rock dissolution lab for each of the 3 groups, acid, neutral, alkaline. And it was mainly to compare the different solutions between the acidic one and the basic solution to see which one would be better used to weather the rock to release more key nutrients into solution.
how you get the alkaline field sites. So for the alkaline group, our field site was in Warner Valley, a little bit outside of Big Gas Ranch, and there you can see a picture that's taking samples there. And where we sampled was a little stream that flowed downhill, and it was surrounded by grasses. And what we observed when we looked was inside the stream were green, stringy microbial rats. And from that, we could see that there was a sign of phototrophs. And so that kind of told us that our alkaline site was in a habitable environment. And we took 2 samples from the site. One sample we took at the top of the stream at the bend, and another sample we took was further downstream. And another thing we observed was that the temperature was higher when we sampled directly at the bend. And so that's basically our alkaline field site. And now I will give it to Mason, who will tell you about our rock dissolution.
During the rock dissolution experiment, we mixed powdered andesite into a mixture of pH 10 cesium hydroxide and held it on a hot plate at a temperature of 60 degrees Celsius. And the photos on the screen are images of that shocking mixture we made. We used cesium hydroxide and held it at that specific temperature to mimic the field sites that Adrian was talking about in Warner Valley. Over the course of the experiment, we took pH and conductivity measurements. And we noticed that the pH decreased from 10 and moved closer to neutral, which is 7. And the conductivity increased. At the end of the 77-day experiment, the alkaline group poured samples of our solution into falcon tubes and put it in a centrifuge. The centrifuge spun tubes around, which separated the liquid from the andesite. And now Kyle is going to tell you about an interesting discovery we found after analyzing the andesite.
After our rock dissolution experiment came to a close, precipitate was found on top of our solution. Precipitate is the solid that comes out of a chemical reaction, and the solution had reacted with the andesite to form to the point where clay was formed. This result was found in the X-ray diffraction patterns of our solution, which you can see right here. X-rays were emitted at our solutions and diffracted off different locations, also shown in this graph. So, starting from the blue one, as you can see, the first spike represents where clay was formed, and that is the alkaline group, which had the best clay, and the next best clay was the acid group, followed by the neutral group with just barely any clay. So, clay forms when water reacts with minerals. This was interesting because clays have also been found on Mars. And if there are clay on Mars, then that must have been was water there also. Since water is one of the 4 requirements for life, we can conclude that Mars had at least one requirement for sustaining life on its surface.
Okay, so the microculture experiment. One of the main experiments that the neutral group had, which was Marissa, Lily, and myself, was the microculture experiment. Just to reiterate, to make a microculture is to recreate the environment or habitat that the organism belonged to and try to make life grow from it. For the neutral group specifically, we tried to make an environment similar to that found at Paddlewheel Creek in Warner Valley.
And the purpose of this microculture experiment was to mimic the different environments in which microbes grow, and also to observe the interactions between rocks, microbes, and plants.
So we sampled from Paddlewheel Creek, a small stream that ran through a meadow in Warner Valley. The stream contained high diversity, high habitability, and large signs of life. At first, we observed green grass, plants growing in the water, brown mats, and organisms in and near the water. From this, we concluded that the site played host to favorable conditions that were perfect for our neutral group. On the other hand, the acidic and acid groups worked at field sites with extreme pHs and temperatures, and there were organisms that were extremophiles, and they were farthest diverse.
So our methods in the field, we were at Powder Wheel Creek, which Marissa just described very nicely. And while we were there, we extracted biological and geological samples using several different tools and techniques. One was giant tweezers, and we used those to pick brown mats and other plants out of the water if they were too far to reach. Also, we used syringes to draw water samples out, and then we put these into sampling bottles that we could later use in the lab.
Another method used in the field was using a pipette to extract various biological and geological material taken from our Powder Wheel Creek samples. We then took these samples back into the lab and inoculated them into our cultures. And the neutral water used in these cultures mimicked the neutrality found in the water at Powder Wheel Creek. And the neutrality allowed for a high diversity of life and habitability. And then we later incubated these cultures for 3 months.
So our hypothesis. We expected to successfully mimic the environment from Powder Wheel Creek because we assumed the neutrality of the water would provide ideal conditions for the sustainability of the organisms. And we knew that our cultures contained the 4 requirements of life, which are right there.
So our results. On the left side of the screen are images taken from underneath the microscope from the original samples from Warner Valley. And on the left side are the images from our own culture that we grew ourselves. You can see that it's mostly green and there's long things in it. And it's just and you can see that there's much diversity and microbial growth there. The reason we were so successful was because our culture was in a closed system and did not have any outside elements hindering the ability for growth to occur. Also, our environment had all the requirements as set, and so it had everything it needed to grow and grow successfully.
So to relate back to Mars, Lassen and Mars both have hydrothermal features and similar habitats. So based off of these, the extreme environments found in the acid and alkaline groups, or the field sites, model previous environments that may have been possible on Mars in the past.
And the fact that extremophiles were able to grow in the alkaline and acidic cultures gives evidence to show that microbes can thrive in various environments that vary in extreme temperatures such as pH. And this provides a database in which future astrobiologists are then able to study similar microbes that may have been present on Mars in the past.
So then in all, overall, 3 experiments of the acidic group, the alkaline group, and the neutral group provide a basis for future scientists to look back and see what they should be discovering on Mars. All 3 groups concluding that clay is a result of rock dissolution provides that from weathering of rocks, the minerals and nutrients that are needed by microbes to survive are found within a clay. So looking up on Mars in the future, we know to look for clay in order to look for possibilities of life. And also, within the culturing of the microbes, it shows us the type of microbes that we need to look for, and those are the fossils that we need to look for evidence of past life. And also within the clay, since they hold the nutrients and the minerals that are needed for microbes, we know that that's the basis to look for those fossils in the first place.
Yeah, let's do 5 minutes of questions.
How high a temperature can these I think you said extremophiles handle?
It depends on the extremophile. Each extremophile is different. Some extremophiles can handle cold, extreme cold. Some can handle extreme heats. The one we were focusing on, we had it at 60 degrees Celsius, which is not like 60 degrees Fahrenheit. It is an extreme temperature. So it just depends on the microbe. And by the microbe, we can also tell what temperature we suspect the area to be, because every area is different for every microbe.
Some have such specific temperature variations, and you can tell what's moving there, what temperature is moving, what's moving. If you see something growing there, you can automatically say what it is. It's because you know temperature.
There was a picture.
Okay.
Sorry. There's a picture that Nikki showed us during the talks that actually, like, it showed you where the specific areas were for which tiles. You can see that there were, green algae and different types of organisms just a few, distance away, dependent on how hot it was and where it was.
Most of us on the practice, 60 degrees Celsius or 20 degrees Fahrenheit.
16 degrees centigrade is 61 degrees Fahrenheit. That's a sort of a central.
4 times, 3 times.
No, 16 degrees centigrade. But I'm a microbiologist, and I want to answer your question. All right. The upper temperature limit for life is around 115 degrees centigrade. But these are archaea, all right, one of our kingdoms of life. And those organisms are chemolithotrophs, as she's talking about. And they're also found in many of the hotter things like sulfur works would have these organisms found there. Sulfur locus is one of these. It grows around 80 degrees. So again, it depends on the organism as to what that temperature is. The upper limit of photosynthesis is for bacteria is around 60, 65 degrees, and centigrade now, centigrade. So we're talking pretty hot stuff here. And some of the eukaryotic green algae that they look at are around 55. So we won't talk about things, but things grow in very cold, icy waters too. So they're extreme files as well.
There's other questions that come up we can have.
Oh, I was just going to ask. So I have a question. What was your favorite part of the project?
Sampling. The drip.
Going out in the field?
The
Tara, the instrument there.
getting to use that.
I should get video.
I think my favorite was the one at Ames, where you guys were. It was really interesting to me, kind of don't believe it's real, so you get to see it.
Are any of you going to become astrobiologists?
No, I'm going to be a cell biologist. I might work with astrobiology, but I'll be a cell biologist.
Who is the other senior? What are you going to do?
Other than working in science, most likely going to biology.
Hooray. That's one of them.
When I go to college, I'll probably enter a biochemical engineering sort of environment. Any questions?
I just want to make a comment, and that is it's generally recognized that people who do astrobiology at some point in their career still have a traditional major or traditional discipline, like molecular biology or engineering for that matter. But then they reach across disciplinary lines and get involved in astrobiology. So we very much encourage them to stick with a major discipline that can have a number of career outcomes, but that if you're up to the challenge of working across disciplines, then astrobiology is something to make a part of your life.
And I'd like to point out that Olivia, as a cell biologist, may someday work with an engineer to plan a space experiment that will be flown on the International Space Station, saying something about the future of human beings in space, in our solar system, and that's part of astrobiology too.
Anything else?
Thank you.
Okay, so, sure. Next, we're going to have our award presentation by Mike Kubo and Steve Zachary.
Get all seats to stand over there. So this is, good evening, everybody. It's good to see you. Good evening, everybody. Thanks for coming. So this is the part of the night where we recognize our students and their accomplishments by giving them their certificate. And we also have some nice pins that of the International Space Station that were provided by our branch chief, Orlando Santos, who will be speaking next. Orlando is actually fairly unique in our group in that he has had the opportunity, the pleasure to work on projects at the International Space Station. So he dug deep into his personal stash of memorabilia to give a nice, a nice pin to the students. So I just want to take a moment before he hands out and just say, this is like Mr. Michael said, this is our 5th year doing this program. And every year it seems to get better and better, but there's something about this year that is really fantastic. The students this year were just outstanding. I mean, I don't think we've ever had 3 seniors in the program that all went on to science disciplines. And this is also the largest year that we've had. It's the most students we've ever had in the program, which has also been really exciting. It's a real testament to you as parents and Bluff High School that we can get so many excellent students to participate in this program. So with that being said, we're going to go ahead and hand out the certificates and a pin here. We're going to start with the juniors. We can go in alphabetical order. So we will start with Marissa Chase. Next we have Lily Fryer. Okay. Next we have Carly Garcia.
Make a photo op here, you guys.
We'll line them up at the end.
There you go.
Perfect.
And we'll take photos at the end also.
I will also say that the neutral group did a great job this year, given the fact that they were without a senior leader. So, good job. Next we have Adrian Hingston.
Absolutely, go ahead.
Okay. Next is Kyle Lemmerman.
You want a picture?
Do you want a picture? It's right here.
There you go.
Okay, next we have Elena Rudnick. Okay, and Adrian Steyer. Yeah, come on, photo op.
Roll now.
You guys work hard.
Neeson, Trujillo. That's all for juniors. Thanks, juniors. And see you next year. Okay, so now we'll move on to the seniors. So this is, again, this is their second year in the program, so it's kind of sad. It's always sad. It's like, saying birds out of the nest, It's exciting, but it's always really exciting to see them go off to college and see what they choose to do. So we'll start with Olivia Henderson. Next we have Justin. And finally we have Jessica Dawson. We would also like to thank our, our partners in this whole endeavor, the teachers here at Red Bluff, our teacher partners. We'll start with Mr. Fred Knoll. And then, of course, Mr. Dave Michael. Thanks. Thank you. And of course, our partner in Lassen Volcanic National Park. Thank you, Steve Zachary. Yes, sure do. And so again, thank you guys. What's that? No, this one's empty.
Wait, we have all the students lined up with
something we need to do first. As a group, we wanted to thank you so much for all your help and being so understanding with all our questions. So we took a picture and it says thank you.
All you guys get there.
Thank you so much. That's so sweet of you. That's really I hope I get to go back next time. I hope you do too. Just the fun. I know tell them how much you want. Okay, because I really it's been so much fun. Good.
Yes, everybody.
Lily, do you want to get the rest? Oh.
And I will say also, these are the kinds of things that make this program so rewarding. Feedback from the students and being able to influence, some small amount of influence on their hopefully scientific careers. We had a real pleasure this year with a student who graduated last year from the program and came back and saw us in the classroom and said that she actually decided to go into science because of the program. And those are the moments that make this extra rewarding.
Yeah, stretch a little. One, two, three.
Hey, Sandy.
Thanks.
It doesn't kill birds.
Touching up your son's hands.
Thank you.
Any more? Okay.
Okay, guys, here.
So next week, again, we'll have our branch chief, Orlando Santos, will speak on NASA opportunities for college students. So this is the natural natural transition to what's next, both for the students and for the program tonight. So thank you.
Can we get the lights back there?
You want them on or on?
Yeah. So, okay. So we can't have a NASA presentation without showing a rocket launch. So this is there's a reason why I'm showing you this. This is the launch of a little satellite from Kodiak, Alaska that we did a couple years ago. And there we go. So the project was called Old Oreos, and it stands for Organism Organics Exposure to Orbital Stress. The other thing at NASA is we always have to come up with a good acronym, right? So we had, some scientists from Ames and from some academic groups, and we built this little thing. It's only about this big, okay? They're called them nanosatellites. And this little package actually had 2 experiments in it. It had an organic chemical exposure experiment. So we were looking at how important chemicals for life are altered in space. And then we also had on board a microbiology experiment where we were actually growing microbes in space after exposure to the radiation environment in space over different times. And so I sort of already went through this. So we had, organic exposure where we looked at some important molecules and what happens over time. We also had 2 species of microorganisms that we exposed to the space environment. And the reason I'm showing this is because this whole thing was done by college students, Santa Clara University students. These nanosat opportunities are growing. More and more colleges are doing these kind of projects. It's an amazing thing for college students to be able to say that they have space flight experience on their CVs. And they really worked on all aspects of this thing, from building the satellite to doing the testing in the lab, and even later on they did the mission ops. They did the communications with the satellite. They ran the show. I mean, it was a great experience. And so I show this as kind of the future, because as you guys move into college, there's a lot of opportunities at NASA to participate in other projects like this. So I have a couple handouts in the back that I encourage all the students to take. One is about what we call the One-Stop Shopping Initiative. It's a website that lists all the student opportunities at all the NASA centers across the country. So you can go in, the website showed up there, it's also on these handouts, so I encourage you to take a handout. But you can go in and register on this page, and you can enter your interests, what geographic areas you might want to work at, whether you want to work at Kennedy Space Center or Ames or wherever. And as you go through this, it ends up sending you all the relevant opportunities that are related to the interest you put in the geographic areas that you put in. So it's really a great tool. There's all kinds of stuff. There's summer programs for college students. There's stuff that you can do while you're at your college that you're going to. Some of the programs provide salary over the summer. Some provide housing at the NASA centers. So there's just all kinds of stuff that, that these folks can do as they progress. I also wanted to take just a second to show you, I have another little handout back here that has the website address too. This has really nothing to do with NASA. This is an organization that was started by some friends of mine at Stanford about 10 years ago, and it's grown dramatically. And what they do is, when you go to this website, when you go to this website, you can enter in, again, what your interests are, and they will match you up with an expert in the field that will act as your mentor throughout your college career, sort of as a virtual mentor, so that you have an email contact with somebody who can help you along in your career, can help you establish contacts in the field that you're interested in. It's an incredibly powerful group. So again, I encourage everybody, all the students, to think about NASA in the future as you go forward in college, and to take advantage of resources like this where scientists you can interact directly with scientists that can help you in your career. Okay? So that's all I wanted to say. Thanks, everybody. What a great story.
Mike, will you get the lights?
Sure. I'd like to thank all of you for coming tonight. In specific, I need to thank a few people as well. When this program expanded this year, I needed help here at Bluff High School, and Fred just stepped in eagerly. If you know Fred, you know also how easily and readily he'll bend over backwards for any student here at Bluff High School. I'm going above and beyond, and he has really done that as part of this program. So thank you, Fred, very much. And also thank you to the leadership here at the school that's allowed us to do this. It's a tremendous experience, a tremendous opportunity. I've learned as much as these kids have the last few years working closely with everyone down at Ames. And I'd like to also thank all the people down at Ames, Sandy, Nikki, Mike, Dave. You work closely with teenagers. You're volunteering to do that. You know, Fred and I, that's our job. You guys, it's not. You know, and for you being willing to do that and eager to do that and being flexible enough to understand the unpredictable nature of it, it's amazing. And thank you very much also for your leadership, allowing you to do that. Because the experience that these kids are getting is just amazing. I also want to thank the interns here. I don't know if you ever know what you're getting into with this program. Okay? It changes. Okay? And these are kids here at Red Bluff High School. If you know these kids, they are involved with pretty much every single club we have here on campus. They're involved in multiple sports here on campus. They are taking AP courses. They are taking college courses. Grades are extremely important to them. And basically this program takes away their free time, takes time away from these clubs, takes time away from their studies. They're not getting paid for it. They're not getting a grade for it. Okay? And they are still eager and willing to do this, and they bend over backwards also to make this program strive and live on. And I think you saw how hard they worked here today. It was just a tremendous experience, I think, for them, basically being able to go through this process and get this experience. And so, thank you guys. You guys have set the bar so high. You set the bar so high right now for the coming years. Part of me now wants to push and go beyond that, but at some point I know it's probably going to be too much, so we're going to have to figure out that balance. So thanks to all of you, and then last people, just all of you for coming here tonight. Thank you very much. You know, obviously the time and energy that these kids put in, and we tried to talk to them today. Don't be nervous. This is your chance to brag, your chance to show off, your chance to get up here and basically show all the hard work that you've done. And hopefully you saw that from me tonight. And we really appreciate you guys coming because you kind of validate what they've done all year. It really makes it worthwhile. I
just want to make a couple of final comments. One is that one of the reasons that motivates us to do this with teenagers is that the big challenges in the future are cross-disciplinary. You have to go to college, you have to learn a discipline, you have to do all that. But the big challenges we face, environmental, economic, but if we want to cross-disciplinary, and that's really what this program is supposed to do, is to get them to think that way. So in the future, it may not be astrobiology, but you're adapting something that's cross-disciplinary. And the second thing is why we work with teenagers, and that is all the stuff that I dream about when I give you this talk, is stuff that will take years to realize. These are the guys, this is the generation that's going to do it. And I think a beautiful analogy is something that Barry Bloomberg, a scientist some years ago, said, and that is that we're in the business of building cathedrals. And when you build a cathedral, it takes centuries. You will not see that cathedral finished. But somebody, a lot younger than you, will be there when it's completed. And that's how we do space science, and that's how we do a lot of things. And that's what motivates us to keep the show going by continuing to bring in people who will carry forward to that dream. So thank you very much for that opportunity. We'll look to the future.
So thank you all. So now I guess questions.
It's not really a question, but my wife and I will comment that we're very proud. I won't embarrass my grandparent of one. how select a group we are to be able to sit here with all you NASA people and all you teachers who are putting forth this effort. This is the only place in the country that this is happening. We're proud of you guys. We're glad to be here.
We feel honored.
If there aren't any other questions, we have time. We're running a little ahead of time. So we can actually give demonstrations of this instrument here, and I want to say a couple of words about it. Not only is this internship program the only one in the nation, but the access that these students have to this instrument is extremely unique.